So my name is Qun Zhou. I also go by QZ. And today I'll be talking about distributed energy resources and the grid interaction. Okay. So a little bit about myself. I graduated in 2011 from Iowa State. My background is really in power systems. I was doing power system and power economics, and after that I joined Alstom Grid in Seattle to develop a market management system for power system. After I left, this all happened when you leave, and then after I left it, it's merged with GE, so now it's GE Grid Solutions. And then I joined UCF since 2015, first as a visiting assistant professor, then tenure track. And again, I'm a trained electrical engineer, but just the focus of my research has shifted a little bit. So now I found that people surround me are most mechanical engineers. So I joined ASHRAE, American Society of Heating, Refrigeration, and Air Conditioning Engineering. And I also have a lab here at the UCF, it's called Smart Infrastructure Data Analytics Lab. I think it's really about smart energy infrastructure data analytics. So that's me, and so I want to talk a little bit about my motivation. I'm always passionate about transforming our energy future. So I guess we all need a sustainable energy future. That's why we really need new techniques and technology that help us move forward to that future. And then also I realized that the clean energy future really relies on every one of us, not only the bulk power grid. So my background is a power system. I was representing mostly utility companies and studying technologies to help improve utility operations and efficiency. But then at the end of the day, each of us use energy, and we need to be aware of how our behavior impact the energy and the grid as a whole. So that's why I'm kind of shifting my focus from a bulk power system to our consumers. A bottom-up approach now, in contrast with to our traditional top-down approach from utilities and power system. And we can do that because of Internet of Things now. Everyone and even every house could be connected, and then we could have lots of information shared, and that can further help us to enhance our energy efficiency. So that's my motivation. So the first application of research of this data in consumer side is really very straightforward about solar power forecasting. Imagine that every one of us or every house has a solar array rooftop. Then we need to operate the solar panels more efficiently. Then we really need to make predictive actions. So forecasting has been done lots of times, but traditionally people build models and put every data into the model, and the output will be coming out directly. So we can build lots of different models. For example, we can do neural network gradient boosting, linear regression, random forest, or time series models, right? But then one question I was really think is that instead of dumping all the data into models, so the modeling, you know, we have lots of mature the machine learning models that we could use, but then we usually do not do quite a lot pre-processing. So, so instead of just dump all the data into the models, can we think it another way, saying, for example, let's look at the solar power and temperature data. We know that they might be correlated, but we don't know how. Instead of dumping all the past, historical solar power data and temperature data into the model, maybe we should look at what are the joint, correlations or joint probability of power in the solar temperature data. Fortunately, there are lots of different ways to estimate, this joint probability. You can use copulus or kernel density estimations, and there are different ways. So we were using copula, which a conventional way to study the correlation would be using covariance matrix, but copula is unique because it captures the entire probability distribution. You can separate each individual. Right now, we only look at solar power and temperature. That's just two variables. You can look at a very high dimensional array of variables and separate them into individual cumulative distribution, and then this method, and we looked at the results. The results shows we tried in different data set, different days of profile, and then most of them shows good results. In fact, we did like 64 cases for different data sets. 90% of them have improvement, around 10 to 20% of improvement. It's shown here. I have to move on now. So the next one, that's the first application. The next application is about smart buildings. Again, we're talking about consumers. So smart buildings. This is where I learned new stuff beyond my electrical engineering background. So this building is actually UCF Global. We simulated UCF Global in the Energy Plus model. This is the thermodynamics heat transfer equation for that building. And then the Energy Plus is a software that that helps understand the whole building energy consumption. So we actually use collecting the real data from facilities. So think to our facility team. We collect the data and then we simulate in Energy Plus, and this is what we had. You can see that our model curve is pretty close to the actual data we collected from facilities. And then now, after we have this, we're asking, what can we do? Use that physical model, and we did one of the optimal optimization is to optimize the HVAC, our AC system on and off status, or occupied and unoccupied status. Normally, we just turn on our AC and sometime around 7, 8 a.m. and leave it all the way until 9 p.m. But instead of that, we did optimal sequencing or scheduling of this HVAC system, and then this is what we found is that we are able to save to 20% of energy. We actually did it, like 2 or 3 weeks ago in UCF Global, and we compare with our base case. Is that we found 20% savings in energy and probably around 30% savings in energy cost, because the cost, utility usually have different time of use rate. Okay, and the last application is really about integrate all of them together. If we have solar panel, we have battery, and then how do solar panels and battery work together, provide service to the grid? So one of the service that grid might need is to smooth out the PV. Now you can see that if we don't smooth out the PV curve, that's the blue curve, it's pretty bumpy, and utilities don't like this because they have to set up all the traditional generating units like natural gas just to sit there standby to account for this uncertainty whenever we need. So what we can do is to use battery to kind of smooth out that curve. But what kind of curve we really target for? So we thought about moving average. When we do moving average, you can see that the curve is a little bit it's smoother for sure, but it's kind of lagging. And then we do forecasting and do a moving average of the forecasted solar power. Then it's smoother too, but it's a little bit leading. So we combine them together, and the curve would track, become smoother, but also track the actual PV generation. So and then we are able to dispatch this battery to meet that target curve. I think that's it. And in the near term, I'm looking to improve the modeling and optimization algorithm, and also coordinate more resources to maximize the usage of solar resources, solar energy. And in the long term, I'm going to look deeper into the probabilistic methods. And I also look forward to some real implementations, hopefully on our campus, and then integrate into courses. And last, I wanted to acknowledge our sponsors and our students. So with that, I conclude my